Hello everyone, I'm Hubert Zhang from EloqDoc. Thanks for joining. Today I'm going to talk about how we are building elastic AI native data pipelines for agentic apps using Apache Pulsar and our document store, EloqDoc. A little bit about myself. I used to be the tech lead of Grimtham at VMware, and I was part of Apache Hawk project as a PMC member. I've spent most of my career in the database world, building large-scale systems. Right now, at EloqDoc, I'm focused on making the database work better for the AI native workload. Here's what we are going to talk about today. First, a quick introduction to EloqDoc and how we think about database architecture. Then, we will look at the data pipeline and the challenges for the agentic AI apps. What makes them different? After that, I will dive into how to choose your streaming and document database. And finally, we will revisit the whole pipeline using a new model. We call it ConvergeDB. So, traditional database, we all know, they were built for the web application, for example. You had one app, one storage layer, no matter it's Mongo or PostgreSQL. But for AI apps, they are messy. They pull in unstructured data, run embeddings, work with graphs, and they don't follow one access pattern. That's why we have been rethinking the entire stack from the ground up, and why we found EloqDoc. We introduced a new database architecture to fit the AI era. We name it the modular database. We break things down into 3 layers: compute, data substrate, and storage. Compute layer is where your API live, maybe SQL, Mongo, Vector, or maybe something else. The data substrate layer is your transaction engine, the cache manager, and your scaling logic, while the storage layer is used to persist your data, and is also pluggable. You can choose the right storage that fits your user case. For example, using object storage to save your money, there is no cross-AZ replication cost. Using Cassandra or StellarDB to deploy in an on-premise environment. Also, using Dynamo for your AWS cloud and Bigtable for your Google Cloud. The real innovation here is the data substrate. You can think it's like the brain of the database system. It handles the transactions, caching, durability, scaling, and fault tolerance. And it's shared across the data model. So we can plug a document engine into it, a SQL or a Vector. And they all get those core features for free. Also, the data substrate is a key to achieve the high performance and low latency for a distributed and transactional database. Okay, let's shift the gear and talk about what the data pipeline looks like for those new AI-driven apps. Nowadays, agentic app data pipeline are very event-driven. They react to the real-time data and persist to streaming services like Pulsar at first. And then this data will be consumed by different data models and stored into different places, like DocumentDB to store financial reports, VectorDB for embeddings, SQL for transactions. Note that each consumer of Pulsar needs to handle its own retry logic, and there is no transaction guarantees between the different databases. Besides, the pipeline often need to push data into analytics platforms, for example, the Snowflake and the Databricks as well. So you've got all these moving parts. They are hard to manage, and everything is eventually consistent, and require separate logic to be error-prone. Besides, event-driven model, what are the main features of the data products in the above pipeline? I think the first is they all need the multi-model. One model isn't enough anymore. Agentic AI apps store data in different databases. The second is the cloud native. You need Kubernetes, you need auto-scaling, you need multi-AZ, and all. Nowadays, more and more people build their applications using web programming and ship it on the cloud in seconds. But remember, cloud is expensive, so you need to be cheap when your apps are idle and be fast when your apps are busy. You shouldn't have to pay a 10 just because your apps may spike in your traffic once a day. So, multimodal is real. Let's take an example. Say you are building a financial trading agent. You have 3 different agents. They will communicate with database and LLM. You may need a SQL database to track the account balance and trades, document database to store the financial reports and contracts, vector database to search terms in the contracts with embeddings, and a graph database to link the company and their relationship. For example, Databricks acquired the NeonDB recently. A simple agent application would require 6 or more databases with different data models. So we need a backend that can handle that variety, or at least make it easier to work with. I will talk about these challenges later. Besides multimodal, the other topic is cloud. It's not a transition from the cloud native to AI native, but it's a convergence. AI and cloud are now evolving together. For example, more and more applications are generated by the web programming. These apps live in the cloud and depends on the cloud native DBAs. For example, Superbase, Neon, and also EloqDoc and Pulsar. But cloud is full of pitfalls. The cloud sounds great until you get the bill. Cross-AZ traffic fees, replication costs, EBS costs, they add up fast. Let's first go through the disk, the storage. Object storage is cheap, but with high latency. EBS is a little better, but it's quite expensive, especially when you try to provision your LPS. Local NVMe is great. It has high performance and low latency, but it's ephemeral. You may lose all your data when your server just restart. So we have to design systems that pick the right trade-off at the right time. Another topic is compute. Compute is stateless, but scale matters. You need to consider how to support scale to 0, which can save CPU and memory resources when your workload is idle. You also need to consider how to scale up and scale out. If scale need to move data on disk, the scale would be very slow. If you are lucky, you have a faster scaling data products. Then you should also need to support the auto scale to meet the diverse of your workload traffic. Finally, let's talk about the network in cloud. It's such a huge hidden cost producer. Cross-AZ fee, cross-region fee, and you also even need to pay the public traffic fee, even if your apps and the servers are in the same AZ. Consider your database use 3 replicas in different AZ to ensure the AZ level high availability. Then you must to pay for the network fee. And consider your client and servers are in different AZ. Then you need to pay the network fee again. We should keep these pitfalls in mind when we are using and choosing the database. Despite the cloud is full of pitfalls, we still need cloud. So what do we really want from our infra, especially for the AI native and the cloud native AI? The number one is scalability. Your ARR shouldn't be limited by your database scalability. Number two is cost efficiency. Run your dev setup for free and your production for cheap. Next, we will focus on 2 types of the data products: the streaming system like Pulsar and document database like MongoDB and EloqDoc. Now, let's first talk about the streaming selection. Kafka has been around. It works, but scaling Kafka is not so fun. Look at the left graph. You add a new broker in Kafka. Since Kafka is a shared nothing architecture, then you need to move data partitions from all the other brokers to this new broker. That would be slow. Expanding a terabyte scale cluster may take hours. When you need cross-AZ high availability, and you're doing the Kafka cluster scales, you also need to pay the cross-AZ replication fee. That's expensive. All the things get worse as your cluster grows. Next, let's talk about Kafka's multi-AZ cost. Suppose you are running Kafka across AZ. I think most of us use Kafka in this way. The producer talks with partition leader, which 2 out of 3 traffic will be cross AZ. As for the replication side, the broker will copy data to other AZ to ensure high availability, generate twice the cross-AZ traffic of producer. So the total is 2 times or 3 times network traffic, which is very expensive. Fortunately, the consumers can avoid generating the cross-AZ traffic by setting some parameters, but the total cost of ownership is still quite expensive. Let's enter the world of Apache Pulsar. Pulsar's architecture splits the compute and storage. Broker is stateless. You can scale out in seconds. No data movement. Just rebalance your metadata. And the storage knows the bucket only handle the new data. Old segments stay put. No need to move the old segments to the new nodes. So all in all, Pulsar is much more cloud-friendly and much cheaper and easy to scale than Kafka. But Pulsar still generates cross-AZ traffic. Now let's take this further with Ursa. Ursa is a new streaming platform created by the Stream Native. Ursa writes directly to the object storage, no local disk. Brokers are stateless and diskless. You can launch new ones instantly. Moreover, it's leaderless. No elections, no failover delays. The client just talks to the broker in the same AZ. So there is no cross-AZ traffic between the client and broker. This is quite different from Kafka and Pulsar. But there is no free lunch. the consumer needs to all the messages of a topic in the correct order, but the messages in URSA now are written by the producer from different AZ into their corresponding brokers. So all the messages shared across the AZ are handled by the object storage, which introduce additional latencies. This is the first trade-off. Also, keep the global ordering. URSA need a cross-AZ metadata indexer. This is the second trade-off. Despite of these trade-offs, I think URSA is still a very promising streaming solution on the cloud compared with traditional Kafka and Pulsar, when user is very sensitive to the total cost of ownership. Note that Kafka recently released the freight cluster, which follows the same idea of URSA to use the object storage to reduce the cross-AZ network fee. I totally agree. The trend of object storage is becoming the de facto of cloud database storage. From the data warehouse to streaming, and now to the OLTP database. We will cover the OLTP database in the next section. Okay, let's move to the OLTP database. I will use document database as an example to show. So Mongo is the most popular database for document. But similar to Kafka, MongoDB is also a shared nothing architecture. Scaling MongoDB, for example, at a shard still need to move your data. It may still take hours for large data set. Besides, config server and Mongo's routers also add complexity. And MongoDB is quite expensive on cloud as well. To achieve high availability, Mongo needs 3-node replica sets. CPU and memory of follower nodes are just used for failover, which is wasteful. Moreover, each replica writes to its own EBS, and EBS is also replicated, which results in the nighttime write amplification. MongoDB's cross-AZ replication also introduced additional network cost. Besides, EBS performance is quite slower compared with local NVMe. You are paying a lot to bring Mongo to cloud. Since Mongo is not designed to be cloud native, you need a cloud native document store. So how to build it? The answer is EloqDoc, a document store that is Mongo compatible, but designed for cloud elasticity. It supports multi-writer. Its architecture decouples the compute and storage. It has scalable redo-log, strong and high performance transactions. Also, EloqDoc is a native distributed database without proxy. The architecture of EloqDoc is clean. The latter part is a computer cluster, which is stateless. It contains a Mongo executor, memory cache, transaction manager, which is data substrate we mentioned before. The local NVMe is used as a cache of object storage. The upper right is a log cluster. It could be deployed together with a compute cluster to save your costs. Log cluster use EBS to ensure data high availability. Data from client first written into the compute cluster's memory and the redo log cluster's EBS, and then responds to the client with low latency. Periodically, the data in memory will be flashed to the object storage for persistent. Object storage will provide cross-AZ high availability for your baseline data. Once data in memory is flashed, the WAL logs could be truncated. This helps to ensure the EBS used by the log cluster is small. since EBS is much more expensive than other storage. Besides, EloqDoc drops all the Mongo overhead. No Mongo's router, no config server, and no replica set. EloqDoc is scalable and elastic on all resource types, including CPU, memory, storage, and logs, to satisfy the diverse workloads. It is the only database that has this capability. We run EloqDoc in the EloqCloud, which is our serverless cloud platform. EloqCloud is the most cost-efficient serverless database, which scales object storage for your data, scales EBS for your write throughput, use local NVMe for your read throughput, and support scale to zero, single compute replica, and so on. To be specific, from the left graph, we can see three types of storage on cloud: EBS, local NVMe, and object storage. EBS is most expensive. For example, EloqDoc uses EBS to store the redo log. Take GP3 as example. Each GP3 EBS disk has 3000 LPS, which often becomes a bottleneck for your write-heavy workload. EloqDoc could scale multiple GP3 disks, but with small size, let's say 10 GB each. This is the most cost-efficient way to scale your write throughput. Next, EloqCloud uses local NVMe as the cache of object storage. It can offer low latency and high LPS compared to EBS. The bottom is the object storage. It can supply the cross-AZ high availability and also have a very good throughput when you need to warm your NVMe cache on computer node when failover happens. Besides storage, we use Kubernetes pods to handle the failover and support one computer replica deployment, one Mongo executor, one transaction manager, and one redo logger. You can save the CPU and memory resources and also avoid the cross-AZ network fee due to replication. So thanks to the new cloud-native architecture of EloqCloud, we can offer the most generous free tier plan with 25 GB storage and unlimited compute hours and up to 10,000 QPS. Welcome to try EloqCloud. Now it's time to revisit the agentic app data pipeline. The traditional model stream events then use consumer to write to multiple OLTP database or push to the OLAP platform. It works, but it's messy. You get a weak consistency between the data models and high end-to-end latency. You also get high operational complexity and need to write code to handle the error case. That's where ConvergeDB comes in. It's one backend with multiple APIs, SQL, document, graph, vector, and more. ConvergeDB supplies unified interface and support cross-model transaction. You can insert a financial report, its embedding, and extract the relationship in the document into document, vector, and graph database, just in a single transaction. So any data model fails, the whole transaction will be rolled back. You will not see empty link to the original report, or you will not lose the relationship between the two companies. Moreover, ConvergeDB can help you to reduce the management overhead. It is a one-size-fits-all solution. So just a quick wrap up. If you are building AI native apps, your data infra should be elastic, multimodal, and cloud native. Pulsar gives you great streaming. EloqDoc gives you a better document store, and ConvertDB ties it all together. Thanks so much for listening. I would love to hear your thoughts and answer any questions. Thank you again.
All right. Great. Thanks so much for sharing, Hubert. That was great.
Thank you.
Okay. All right. Okay, so we have a handful audience. Let's see if we have any questions for Hubert. Okay. All righty. Okay, we'll give it another couple of minutes to see if any questions from the audience. All the recordings and then PDFs will be uploaded, and then you can watch after the summit is over. All right. Okay, so we got a question. Let me read it. How do you think about knowledge-based agents? Hubert? Okay. I think there's some network issues. Okay, yeah, I think we probably lost him due to network issues. But we will get this question to him and I will get it addressed. Oh, all right. It seems that Hubert can type out the answers.
Oh.
All right. Okay, I'm also gonna turn off my video if it helps with the streaming. Okay. Can you hear us, Hubert? Okay. I'm gonna read out the answers and then share with the rest of the team. Okay, so basically Hubert's answer is for agentic applications, data is the fuel. Even small apps with few users need rich data sets to power RAG pipelines, build knowledge graphs, or connect pools via MCPs. These apps rely on multiple data modes, SQL, Mongo, Redis, vector, graph, and managing them separately is hard. Worse, there's no easy way to guarantee interactions across models, but transactions make life easier. That's why we're building a new converged database to unify data models and bring cross-model transactions to agentic apps. All right. Hope this addressed the question. Okay. All righty. If there are no more questions, I'd like to thank you for Hubert again for his time and sharing his expertise. And thanks for everyone who's joining. Please remember to take the survey and win the prizes. Alrighty, we'll give 1 minute back to everyone, and I'll see you guys in the next sessions. Thank you. Bye.